In this lesson, we are going to talk about linked lists, how we implement them and what they're used for, or at least two of the uses for linked lists. Okay, we have been looking at different ways of holding data earlier. We started from a simple variable and then looked at arrays that can hold a lot of the same type of data. And then we introduced records where you can group together related information of different types of data. And we showed how arrays of records allows you to easily manipulate the data together. Now we're going to study another way to hold related info, which is called linked lists. So in this module, we'll introduce the concept of linked lists, compare structuring data using arrays of records and linked lists. And after this module, you should be able to explain the notation of linked lists, state the advantages of linked lists, and also the disadvantages of linked lists. Okay, linked lists at first glance can seem very similar to arrays or records, but let's look at the actual differences. Okay, first of all, in arrays, is the data directly related? Not necessarily, it's just that the data is of the same type. The array of records, the data is actually related. What we mean is that, as we saw in last week's lecture, you actually connected the data together that belongs to the same entities. Like, for example, the student's name, the student's ID, the student's CGPA, all can be stored into the same record, and then that record can be put in an array. Well, with linked lists, same thing. You actually have a record of data that is related. You can put it, of course, you can also just have a linked list of just single data, but linked list does allow you to have a whole record just like arrays of records. Now, the memory in arrays is contiguous. That means everything is one after another. It's connected. The first one, the second one is right next to each other. Array of records also is the same way. It is contiguous. The first record, the second record, they're all right next to each other. In linked lists, they do not have to be contiguous. They can be anywhere in memory that belongs to that program. So you can access the memory in different places, okay? So that means that you don't need to allocate one large block of memory that's right next to each other, like with arrays and arrays of records. Now, in arrays and arrays of record, the accessing of the data is random access, meaning just give the index and then you can jump straight to the particular array location or the array of record location. Linked list, however, is sequential. It's like a list of things chained, like a chain. You know, you have to go from one chain, one link to the next link to the next link. Okay, so it's sequential. And the size of arrays is fixed. That means you allocate it, then that's it. Same with size of array of records, you allocate it and that's it. Of course, you can reallocate, but that means doing a lot of copying. Linked list is dynamic. What you do is you allocate one link at a time. That means you don't have to know ahead of time, I want 100 records. Or I can just say, oh, I just allocate the next record. Then after some time, I say, allocate the next record. After some time, you say, allocate the next record. So then it will not be fixed size. It can just keep growing as long as your computer still has enough memory. So for example, in a linked list, in an array, you have just one type of thing, time array, and then the float distance array. Whereas in an array of records, you can put the time and the distance together. Even though they're different types, you can put it together into the same record, and then you make an array of the records. With linked lists, however, you put into the record this special pointer, okay? And then you don't have to make all the records at the same time. In an array of records, you have to make, you say, I got 30, then you make 30. And after you run out of 30, cannot already. If you make a dynamic array, then you allocate more, you have to copy everything. Linked list is not like that. And then here we have another example. name 840, so it's 800 records of 40 characters each. And then student 800, mark 800, letter grade 800. So array of records, we put it all together into one record, and then we make the array, right? Remember from the last lecture. In linked list, we put it all together in the record, but we have a pointer. And then we don't have to say how many we need. We can just keep making more as we need it. Okay, the notation. The fundamental unit of an array is the element, and then you have the first element and the last element. Whereas in a linked list, the fundamental unit is a node, and then you have the head of the list and you have the tail of the list. Arrays, records, and linked lists, how do they look like arranged in memory? So arrays, right, all the same type data all stuck together. So here are the names all stuck together. Here are the IDs all stuck together. Here are the grades all stuck, here are all the marks all stuck together, and here is the letter grade all stuck together. Array of record is better. You have each student's information together, but for both arrays and arrays of records, it's fixed size. If you allocate 4, that's it. 4 is 4, cannot be more. Linked list, you have each student's information stuck together, but instead of having to be fixed with a number, you have a pointer going to the next link, to the next link, to the next link. So if I want to add one more, I just allocate one more and I add to it. So why should I use linked list? At first glance, it seems like, isn't it easier just to make an array of records? After all, everything is stuck together already. It's organized properly. So that means that I don't have to run around looking for the pieces. They are all actually put together. But, arrow next. Firstly, linked list is its dynamic nature. Remember, we said array, once you allocate a size, that is the size. Even if you have the special dynamic arrays that you can reallocate a bigger array, you still have to copy all the data over. And the other thing is that in a linked list, you can add, delete, and sort without copying. You can just put things, you can put things in between in the links. So what do we mean? Let me show you. If you have an array, right, and we wanted to delete somebody from this array, something from this array. Let's say we want to delete Jin Ling from the array. So when I delete him, he's got this blank there, which is not acceptable. So you have to copy Navina's information up one step. Then you have to copy Xiaoming's information up one step. Which means that in the end, you have to copy 8 times just for this linked list, or just for this array of 4 students only. Just 4 students, and we delete the second student, we have to make 8 copies. Can you imagine if we have 100 students or 1,000 students, then there's going to be a lot of copies to be made. Deletion in linked list, on the other hand, all I have to do is bypass Jin Ling. That means that instead of Hadrami going to Jin Ling, then going to Navina, I just bypass Jin Ling, go straight to Navina. So, which means there's only one copy. Okay? There's only one copy. Insertion in array. Let's say now we need to insert. That means we need to move Xiaoming down. Then we have to move Navina down. And now only we can put John in. Which means I've got 12 copies just to put John into the second spot. With linked list, I just have to put John in and link it. So instead of Hadrami going straight to Navina, now Hadrami goes to John and then John goes to Navina. Which means that we only need to make 6 copies. Okay? 6 meaning that this pointer needs to point to this place now and this one copy there. Then you got this data. Okay? So, linked list has these advantages. It is dynamic. See, if an array is full, you cannot add any more element. So you must allocate extra space that is not used for a long time, or maybe not used at all, if you never use up all the space. Secondly, you only need to copy the new element. You don't have to keep following all the elements down and copy. So like if you have 800 students and you add an element in position 10, that means that you have 3,160 copies, okay? So that's a lot of copies just to add one student in position 10 when you have 800 students. Now the disadvantage is that, remember we said that arrays have random access. You have an index, you can jump straight there. Okay, I want to access element number 100, I just jump straight there to element number 100. So, whereas linked list, you have to follow the links. Go through the first one, then the second one, then the third one, fourth one, and find until we get to element number 100. So it's slower sequential access. And every record needs to have that pointer to point to the next record. So it uses a bit of extra memory. So the memory usage is slightly less efficient because you need to have that pointer there. So, okay, now that we've heard of linked lists, how do we build one? Okay, so we're going to show you how to build a linked list. We're going to build a simple linked list. We're going to introduce other types of linked lists and use a linked list to implement a stack, and then use a linked list to implement a queue. Okay, so we're going to show you a basic linked list. So in this module, we will now set up a simple linked list, and instead of having a lot of data just to complicate things, we just store one character. Of course, if you want to store more than one character, you just have to add more things into the record, that's all. So after this module, you should be able to define the structure of a linked list, create a simple linked list, and print the members of a linked list. Okay, so this module's code is going to implement a linked list of characters, and so you need to define the structure of the record that you're going to make, and you use a function to reserve memory for a single node, and then initialize the data in that node, which in this particular case, we are just going to be one character. But if you want to do more than one character, it's just a simple matter of adding more variables inside the record definition for that node. So then you repeatedly call this function to build the linked list. And finally, we'll use a while loop to print out everything in the linked list. Okay, this is what you should be thinking about for this program. What are the parts of a linked list? How can we visualize what is happening in this linked list? How do I define a structure for the linked list? How do I create or reserve memory for a node? And in general, how many name pointers and variables do we need? Okay, this is the sample linked list program, linkedlist.cpp. And it's just going to create a simple linked list and then print it. Okay, most of my examples are going to be adapted from this book, Structuring Data and Building Algorithm and ANSI approach, that I wrote with Professor Jonathan White back in 2006. Now you are using C++, so I have been translating all the examples into C++. But essentially, the C++ example and the C example are quite similar. Okay? The main thing that we are doing is we are using the C++ C out and stuff like that. And also making memory, we use the C++ new rather than the C malloc. Okay, so anyway, here is the code. Okay, first we have this record that we define what is each node going to look like. So we put the data, we're calling it key, it's of type character. So if you want to have more data, you just add more data here, okay? For this one, just for simplicity, we're just going to have one data, which is the character key. The important thing here is that we have this pointer. The pointer is of the same type of the record. You see, the record is called struct ll node. The pointer is also struct ll node, but pointer. So the star there tells you it's a pointer. And what it does is we call it next. Why? Because it's going to point to the next node in the linked list. It is like your link going to the next node, okay? And then we have a function prototype here to tell us that there is going to be this function that will return a pointer to a node, okay? And we give it the value that we want to put into that key, okay? Then we have this main program, which it's going to need a pointer for the head and a pointer for the current. Now at this point, we just made the pointers. We haven't yet declared the variables. Okay, that means that the nodes haven't been made yet. It's only a pointer. Okay, now we ask it to make a new node that has the value of the character now. Okay, this is the now character. Now character is different from 0 because the character 0 has a particular ASCII value, which is not 0. But the now character has the actual value 0. Okay, the value 0 and the character 0 are two different things. So we're using the now value to indicate that this is a head node. Okay, then we're going to put the current pointer also at the head because right now the list is still empty. Then we ask the user to enter 3 characters and we have a for loop to get the user to enter the character. Then we make a node and connect it to the linked list. And we repeat that. Then after that, we move the current back to the head so that it will start from the beginning and we print it all out. Okay, we print it all out. So each time we go to the next node like this and we print it all out. The init ll node function, what it does is that first it makes a temporary variable to store a new node. See, this is memory allocation. This memory allocation says to C++, please give me enough memory for this new node. Then it says that we're going to initialize the next pointer to now, and we're going to initialize the key to the value passed in. Then we return this pointer back to the calling program. When we run this program, you see something like this. Actually, you will see longer addresses because nowadays we use the 4-byte addresses. But because 4-byte addresses whole string, long string of hexadecimal, I have retained the old 2-byte addresses for this illustration. The principle is the same. It's just that instead of only 4-digit hexadecimal, you're going to get 8-digit hexadecimal, which is a lot harder to eyeball. Okay, so that's why we retain the old style 2-byte addresses for this example. But the principle is the same. The positions of these nodes may be contiguous or not contiguous. It doesn't matter. They can be anywhere in memory. And the last one will be now, so that it tells you this is the end of the list. That means that the first node is here at 07cc. Where can I find the next node? I can find it at 07d4. So I go to 07d4, I find the next node which has the J. And the next node to that is at 07dc. I go to 07dc, I find the next node has the O. And then the next node I follow is 07e4. I go to 07e4, I find that it has the N. The next node is not there. There is now. Now meaning that there is no next node. Okay, there is no next node. Okay, so what are the parts of a linked list? How can we visualize what is happening? How do I define the structure of a linked list? How do I create or reserve memory for a node? And in general, how many name pointers and variables do we need? Okay, what are the parts of a linked list? Firstly, we have the head of the linked list, which essentially is letting us have the handle to hold on to the linked list. Okay, it tells you this is the start of our linked list. And then we have the boxcars which carry the information. So we actually have the real data inside here. The head, usually the head node just has dummy data. Like in our case, we use the character, the null character, okay? And then in a lot of cases, we will have a tail node also, okay? In our example just now, we didn't have a tail node, but you can have a tail node which is like the caboose, which just marks this the end of the linked list. So how can we visualize what is happening? The best way is by a VP diagram. When we are dealing with pointers especially, VP diagrams are very helpful. So let's look at this visualization of the VP diagram. I made a YouTube.
This video illustrates what happens in the linked list program. As usual, the program starts at main. So we will scroll to main. First, we initialize the variable j to 0. We declare a character variable called val. Declare the head pointer. Declare the cur pointer. We now call init_ll node to create the head node. It does this by first declaring a temp pointer. Then it allocates memory space for the new node. Now, it initializes the next pointer to null, and the key to the value sent by the calling program, and returns the newly created node. We now start by pointing the cur pointer to the new head node. Ask the user to enter 3 characters. Use a for loop to get the 3 characters. Get the first character. Ask init_ll node to create a new node with the first character. The new node will be pointed to by cur arrow next. So in init_ll node, we again use the temp pointer to allocate space for the new node, and initialize the next pointer to null, and the key to the value passed in, and return the address of the new node, which is stored in cur arrow next as noted earlier. Now we move cur to the new node. Back to the loop. Get the next character. Ask init_ll node to create a new node with the next character. Use the temp pointer again. Allocate the memory for the new node. Initialize the next pointer to null. Copy the character into key. Return the address of the new node, which is stored in cur arrow next. And we move cur to the new node. Finally, for the last round, get the last character from the user. Ask init_ll node to create the new node. Use temp. Allocate the space. Initialize the next to null. Put the value into the key. And return the address back to cur arrow next. Advance cur to the new node. Now we move cur back to the head so that we can print everything from the beginning. Print the header. Loop until cur is null. Null is pointer 0, which is the same as false, so this loop ends when cur is null. Print the address of the current node. Print the key value of the current node. Print the current node's next pointer address. Advance to the next node. The current address is still not null, so we loop again. Print the address of the current node. Print the key value of the current node. Print the current node's next pointer address. Advance to the next node. The current address is still not null, so we loop again. Print the address of the current node. Print the key value of the current node. Print the current node's next pointer address. Advance to the next node. The current address is still not null, so we loop again. Print the address of the current node. Print the key value of the current node. Print the current node's next pointer address. Advance to the next node. The current address is now null, so we are done.
Okay, let's take a closer look at what's happening. Here we declare pointers for the head and car. Now, these are just pointers. Right now, they're pointing at nothing, at null, okay? So we indicate null here with these ground symbols. Head points to null, car points to null. That means there is no node there yet. Okay, there are no nodes, it's just a pointer. Then, we call init LL node to create an actual node. For this example, let's say that the value is j, okay? So we start here at this init LL node, and we declare a variable, a pointer variable called temp. So temp is a pointer, it's not pointing at anything yet. The next step, however, we create some memory. We ask C++ to allocate some memory for the node. And how much memory is based on this struct LL node. So struct LL node, as you recall, had a character and a pointer. So the node here has a character and a pointer, and we're going to assign its address to temp, which means that address is pointing to this new node. Then we say temp arrow key equals var. What does that mean? That means that look at temp, look at the node that it's pointing to, which is this node, and look at the key, which is this part, equals val. That means take the value of val and put it in there. So value of val is j, so j gets put in there. Then temp arrow next equals null, which means that looking at temp, look at the node that it's pointing to, which is this node, look at the next part of that node, which is this pointer, and assign it the value null, which we signify in VP diagrams with a electronic ground symbol, just like this. So this is showing the result of these two actions. Then we return temp, so we return the address pointing to this new node. So in the main program, we had said init LL node null, the null character. So if the null character, that means that instead of j, it would be null character pointing it, put in here. And the result that is given to head. So now head points to this new node, which contains the null character, and is followed by nothing by the end null here. Then we say car equals head. That means we copy the address that's stored in head into car, which means that now car is pointing to the same node that head was pointing to, which is this node here. Okay, then we want to start building the linked list, which means that we ask the user for a value, and let's say the user type j. If the user type j, then we say car arrow next equals init LL node val. That means that car is this guy, arrow next, which is, arrow means that we're going to now look at this node, and the next, which is this pointer here, equals init LL node. So we call init LL node, which makes a whole new node, initializes it to val, which in this case is j, and initializes the next to null, and that value gets given back to car arrow next. So car arrow next is now pointing to this guy. Then we say car equals car arrow next. Well, remember, what's car arrow next? Car arrow next is pointing to this guy. So if car equals car arrow next, that means that this guy gets copied here, which is this guy gets copied here. So this is now pointing to the new node. So head is now pointing still at the head node, but car is no longer pointing at the head node. It is now pointing at the new node. So we keep doing this. The user enters O, then car will go to the O, then the user types N, then car will go to the new node N, and it will end up looking like this. So you may be wondering why we need to have two pointers. Well, the fact is that you notice head never moves. Head always points to the head node. But we needed to keep reaching down into the list, right? So that's what car was for. Car moves. It was first pointing here, then it's pointing here, then it's pointing here, then it's pointing here. So we don't lose track of the head. We use car to move. Okay? So the car moves, the head stays the same. And that way we never lose the head. Because if you didn't have car and you were moving the head, then you lose the earlier ones. Nobody's pointing to them, you can't get there anymore. Okay? That's why we need two pointers in this particular case. Now, how do I define the record of a linked list? It is the same format as a record. Okay, so you've got your struct name, the struct tag, and then the data you have inside. You can have more data inside, but you need this pointer that points to the same record. So it's struct LL node here. So if it's struct LL node here, then it's going to struct LL node here. If it's struct student here, it's going to be struct student here. If it's struct car here, then it's going to struct car here. If it's struct elephant here, then it has to be struct elephant here. Whatever. Okay, it has to be the same. And then we use a name that makes sense. And since this is a node that follows to the next link, so we call it next. Okay, that's why we call it next. Next is not a special word. If you're writing this program in Malay, you call it kemudian, for example. But it doesn't matter. It doesn't matter to the computer. It matters to the human. Okay, humans want to know what they're reading. But to the computer, it doesn't matter. It's just a name. Any name, as long as you always use the correct name, then the computer is fine with it. Okay, so that this pointer will point to another node of this same type. So how do I create or reserve memory for a node? We use the new keyword in C++, new, and then the node. Okay, this is what we use in C++, which is different from C. C used the malloc. How many named variables and pointers do we need? Well, how many do you think? 3 variables? 2 variables? 1 variable? Actually, we don't need any named variables. But how about pointers? How many pointers do we need? We needed 3 pointers to keep track of everything. 1 for the head, 1 for the tail. Now, in the case that we just did, we didn't need that tail pointer because we never try and do anything more with it. But very often you need that, as you'll see later. And 1 for the current node. You need that to move around. Okay? So in summary, linked lists are best visualized using VP diagrams. If you don't draw your VP diagrams, then it's almost certainly you will get confused and write the wrong code. So actually, how you remember this code, you don't. You don't remember the code. When I'm trying to write it, I don't try to memorize the code. What I do is I draw the diagram, then I create the code. I create the code based on the diagram. Because on the diagram, you can see I need to connect this to this, I need to connect that to that, and then you write the code according to the diagram. Okay, there are different ways to do linked lists. So we're going to look at some of the main types. Okay, in this module, we're going to look at VP diagrams of the structure or main types of linked lists. And after this, you should be able to sketch a basic linked list, sketch a circular linked list, and sketch a doubly linked list. So a basic linked list, this is the one that we saw just now. We have a head pointing to the nodes, and then it just ends there. This particular example doesn't have a head node. The head pointer just points to the first node without a head node. And you can have ones that have head nodes, and you can have ones that don't have head nodes. And the big difference is that if you do not have a head node, you need to say if. If the head pointer is null, then you need to add the new node, rather than just following the head arrow next to add the node. Circular linked list, that means that the last one points back to the front. And here you can actually get away with not having a car, because your head can just move around and you'll still find its way back to the front. Doubly linked list means that we can go this way and we can go that way because there are links going backwards. So you have a next pointer and you have a previous pointer. And there again, you could get away with no car pointer because your head pointer, or actually you can get away with no head pointer because your car pointer can move back and forth and back and forth. See, with a singly linked list, once you move away from the head, if you don't have something pointed to the head, it's lost. But this one, because you've got pointers going back, so you can go back and forth and back and forth. Okay, so now we're going to look at using linked lists to do something. And the somethings are, the first something is a stack. Okay, we're going to look at what actually is a stack, how to implement a stack using a linked list, and also then you will be able to tell what is an application of a stack, how to use a VP diagram to explain a linked list implementation of a stack, and how to write C++ functions to create a stack, push into a stack, and pop from a stack. Okay, so this actually is the simplest thing you can, maybe it is the simplest thing, at least it's definitely one of the simplest things you can do with a linked list. It only has two fundamental operations, which is to insert a node immediately after the head, which is called push, and to retrieve and delete the node immediately after the head, which is called pop. And what is a stack? Well, it's like you have a stack of bowls. Okay, you have a stack of bowls. The bottom one is the first one to put in, but it's the last one to be taken out. Because what you do is you'll just take from the top, right? So you pop something off the top of the stack, and then you push a new bowl on the top of the stack. And so to get to the last bowl, you have to pop, 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 pop to get to it. Okay? And an example of use of stack is in the RPN calculator, which is called the reverse Polish notation calculator. And it's used by many engineering calculators in the old days. Now, nowadays, the modern engineering calculators, they use infix notation. But in the old days, there was a lot of people who preferred this reverse Polish notation calculation because it lets you do faster entry than conventional algebraic entry, because you don't use parentheses. You don't use these parentheses. So for example, if you want to calculate this, what we do is say 5, enter, 2 minus 6 times. So what happens in a stack is that you push 5, and then you press enter. So then you press 2, the 5 pushes the 2 down, and then you press minus. So it takes those two numbers and subtracts them, and you're left with 3. Then you push 6 on top of the stack, and you press times. So it takes those two and multiplies it. Okay, so this is an example of a reverse Polish notation calculation. And this is called postfix calculation. So what are these two, LeFou and FIFO? Are they like hobbit names or something? You know, LeFou, FIFO, Bilbo, Frodo? No, they're not hobbits. LeFou is last in, first out. And FIFO is first in, first out. So which type do you think a stack is? You think about it. When I push something on a stack, and then I push something else, what do I get? I take the topmost one, right? So a stack is a last in, first out, right? What about a queue? Okay, a stack is last in, first out. A queue, you get to the queue, the first person at the queue, the second person, the third person, they will serve the person who came first, right? So that one is first in, first out. All right? So a stack is a LeFou structure, and a queue is a FIFO structure. Okay, so now we're going to look at how to implement a stack of characters with linked lists. And remember, if you want to have more than just characters, it's a simple matter of adding things to your record. So we will actually use sections of our previous linked list example. We'll use the same record definition, struct LL node, and we'll use the same init LL node function to allocate new nodes. But we're going to have 3 new functions. Empty, which says, hey, is this stack empty or not? Push, which is say, okay, I want to push something new onto the stack. And pop, which is to remove something from the stack. And always the top thing. Okay, you always remove the top thing. Okay, so how can I visualize what's happening in this program? How do we start to prepare building a stack? How do we push a character into the stack? How do I pop a character from the stack? How do I know if the stack is empty? And is a linked list the only way to implement a stack? Well, so let's look at this program, stack.cpp. We have defined push to be 1 and pop to be 0 so that we can use the names rather than just having 1 and 2. Okay, so instead of having to, sorry, I said push to be 1 and pop to be 0. No, I mean pop to be 2. Okay, so push to be 1 and pop to be 2, and that way we don't have to remember it's one push or it's one pop. You know, it's just, we just use the names. And then we have that same LL node, struct LL node from before, and now we have function prototypes to this LL node thing here. Okay, it's a init LL node. That's the same as last time, the previous lectures, the previous sections. And then we have empty, which says, hey, is this stack empty or not? And it takes the head node and the tail node. And there's a push which says, okay, let's push something onto the head. And there's pop, which is then get me the thing off the top of the head and return it. Okay, then here we reserve memory for the address of the head and the tail, okay, but we haven't yet put anything there. So that memory is whatever random thing happens to be there. And then we create two null nodes. Now we put something there. We put a head node and a tail node. And the head arrow next points to the tail. So that means the head node will point to the tail node at first because there's nothing in the stack. So from the head, you get to the tail with no data. And the user gets to choose whether they want to push or pop. And here it calls the function push to push if you ask for push, and it checks to see if it's empty, because if it's empty, you can't pop. So if it's not empty, then it pops. So this is an example output. It all depends on what the user inputs. See, so if the user presses 1, which means push, then it asks you what you want to push, then you say N, so then N is pushed, then you press 1 again, and you push what? And A, okay, A is pushed, then you press 2 again. No, then you press 2, which means pop. So the A, which was pushed last, is popped. Then I press pop again, then the N, which was pushed last, is popped. And if I try pop again, it says, sorry, cannot. Stack is already empty. Then I can say 0 to finish. So let's look at the VP diagram animation. And again, the animation is based on the old C version of the program, but it's pretty much doing the same thing as the C++ version.
This illustrates the stack program. This stack program is implemented using linked lists. The linked lists used in this program are singly linked lists. As usual, we start at main. 2 character variables, value and what, are declared. Then the head pointer. Then the tail pointer. It calls the same init LL node that we saw before in the linked list program to create the head node. So it declares the temp pointer. And allocates the memory for the node. Sets the key value. And nullifies the next pointer. Then it returns the address of the new node to the head pointer. Now it does the same for the tail node. The declaration of temp. The allocation of the memory. The assignment of the key value. Nullifying the next pointer. Returning the address to the tail pointer. Point the next pointer of the head node to the tail to complete the empty stack. Now we loop, asking the user to enter push, pop, or end. This while loop actually just keeps reading until the user types something that is not a space or tab or carriage return. What was typed was a character, so we subtract the ASCII value of 0 to turn it into an integer. The user had typed 1, which means push, so we ask the user what they want to push. Again we keep reading until the user types something which is not a space or tab or carriage return. Then we call the push function to push that into the stack which is pointed to by the head pointer. The push then declares a temp pointer to store the new node. And calls init LL node to create that node. Init LL node does its usual of declaring a temp pointer, Note that this is a different memory location from the temp in push. It then allocates the memory for the node and inserts the value into the key and sets the next pointer to null and returns that address to the temp in push. Then we connect temp's next pointer to what head's next pointer is pointing to and point head's next pointer back to temp. This means that we now have a new node in the stack, as you can see from the VP diagram. Now it prints that the character was pushed and continues looping until the user types 0. So since the user did not type 0, we go back to the top and ask the user again and read another command from the user. This time the user typed 1 again, which means push. So we ask the user what they want to push and the user types a character. So we call the push function to add that character to the stack, which then uses a temp pointer to receive the results of the call to a init.ll node, which then declares its own temp pointer and allocates the memory and puts the value into the key and null in the next pointer and returns the address to the temp in push. And then temp arrow next is pointed to head arrow next and head arrow next is pointed to the new node at temp. Then we return to the main program and print that we pushed the new character. So since it's not 0 yet, we ask the user again. And this time the user told it to pop. So the switch goes to case pop, which then checks to see if the stack is empty or not, by seeing if the head node's next pointer is pointing to tail. Since it's not, we return 0, which means false. So back in the main program, it goes ahead to call pop, which declares a temp pointer and a character variable, and retrieves the key from the node at current's next pointer. Then it points the temp pointer at that same node and moves the current's next to the next node. Then we release the memory of the node which we want to remove from the stack, so that the memory can be reused and not wasted. It then returns the value we saved earlier from that node's key to the main, which stores it in the variable value and prints it. Since the user's choice isn't 0, we loop back and ask the user again. And the user types 2, which means pop. So we check to see if the stack is empty. And since it is not, it returns 0, which means false. So the main program now calls pop, which uses a temp pointer and a character variable val, and stores the key in the node pointed to by the current's next pointer. Then uses temp to keep track of that node and makes current skip that node. Then it disposes of the node, freeing its memory, and returns the value of the key back to the value variable in main. Main then prints the value and repeats the while loop, asking the user for the next task. The user types 2 again, which means pop. So it checks to see if the stack is empty. And the head's next pointer is already pointing to the tail, so it is. So it prints stack empty and goes around for the loop again. So it asks the user again what to do. And the user types 0, which means end. So it doesn't loop again and says program finished.
This is the same init.ll node that we used in the earlier linked list program. This code checks to see if the stack is empty. The way that we tell that the stack is empty is the head node is pointing next to the tail node immediately. That means the head node is connected directly to the tail node. That means that there is no data in between. That means the stack is empty. This is the push function. The push function calls init.ll node to create a new node, and then it connects the next of that new node to the head arrow next, because we always add the new node to the head of the stack. Then it connects the head arrow next to the new node. So now the head is pointing at the new node. So it goes from the new node, It goes from the head node to the new node to the previous first node. This is the pop function. The pop function first keeps the value of the key, that means from the current position, next key. Okay, save that key because that key we will want to return later. Then we say current next equals current next next. That means that we're going to skip the current top function, the top node. We had saved it here in using temp so that we can get rid of it later. So after we've skipped it, then we will go to delete that previous top node. That's why we needed to store the value in val, because once it's deleted, it's gone. So that's why we need the val here that we can return then to the calling function. Okay, how can we visualize what's happening in this program? How do we create a stack? How do we push into the stack? How do we pop from the stack? And how do we know if the stack is empty? And also, is a linked list the only way to implement a stack? Okay, how can I visualize this, what is happening in this program? Think of it as a train, right? So we have this struct LL node head, struct LL node tail. So the head node and the tail node, and at first it's, and we initialize it to null to indicate that it's the head and tail node. Then at first we connect head to the tail. So that means the head is connected directly to the tail. There is no data in between. So how do I create a stack then? I have the pointer, head, the pointer, tail, and we create a node to put for the head, and we create a node to put for the tail, and we connect the head to the tail. Okay, the head node, arrow next, goes straight to the tail, and there's no data in between. So you can see these are the parts here. And the head arrow next goes straight to the tail. Okay, how do I push onto a stack? We've got struct LL node is star temp. Okay, so this is again a temp pointer, and we have temp equals int LL node val. So we make a new val node. Okay, so the val was a, so we're going to put a in the node, and then temp arrow next equals head arrow next. Okay, temp arrow next, so this one equals head arrow next. Head arrow next was like this, right? So it's going to point also to this end here, and then head arrow next equals temp. So head arrow next, which used to point at the end node, now it goes to the a node. So we have inserted this a at the head of the stack. Then how do I pop from a stack? Well, we want to remove the top of the stack, so this is the a here. So we have this temp pointer holding onto the a. In the meantime, we store the value from here, put it into val, and the temp, which is holding onto here. Then we bypass this one. So we say head arrow next, which is this pointer, is now pointing to head arrow next, head arrow next, which is this pointer. So which means that we copy this pointer over to here. So this one is now pointing straight to here. Then we delete temp and get rid of this node that we don't need anymore. How do I know if a stack is empty? Well, the way that we used in this code is head arrow next equals tail, right? It's connected directly to tail, nothing's there. We could also say head arrow next equal key, because if you look at here, the key is now. So head arrow next key is now. That means that the head's going to the tail, because if there was something there, it would not be now. It would be the whatever value was there. Another way is to say head arrow next is now. That means head arrow next. That means this pointer here is now. So whether the key is now or the next is now, both of them mean that you have no data in between. So is linked list the only way to implement a stack? Well, no. Arrays can also be used, and this is called a contiguous stack. The main problem with that is that you have to reserve enough space in that array to accommodate as big a stack as you think you will ever need. So now you should know what is a stack and at least one application of a stack, draw VP diagrams of a linked list implementation, and write C++ functions to create a stack, push a node, pop a node. When I taught this in face-to-face class, now you said, wait a minute, what do you mean you taught this in face-to-face class? Isn't this the first time you're teaching this subject? Well, yes, it's the first time I'm teaching this diploma subject, but long, long ago, in a faculty not so far away, Faculty of Engineering, I taught this class to engineering students. We were using C rather than C++, but it's pretty much the same class. At that time, we had, what I would do was I would call out students, and then I would call students out to act it out, and that helped them understand the code better. Now, unfortunately, we are having to do all this online, so I can't call you out to do this. So what we did actually in preparation, you might say, you mean back then you already anticipated that there was going to be a pandemic? What are you, some kind of prophet? No, I'm not some kind of prophet. Actually, the reason we originally did these animations was because we said, some students came up to me and said, hey, it's great that you had us come out and act things out. It helped us understand things better. But we can't go back and revise those acting out. So that's why we made some cartoons of cartoons acting out the program, and that way you could actually perhaps then you can watch it again and again.
One of the simplest practical applications of linked lists is in the building of stacks. In general terms, a stack is a type of LIFO structure where LIFO stands for last in, first out. In other words, the last element added is the first to be removed. This is how we set up the linked list. First, we declare a head pointer and a tail pointer. They are both pointers to struct LL node. Now, we call init LL node to create a new LL node and make head point to it. This is the head node, which has a null character in it. Then, we call init LL node again and make tail point to this new node. This is the tail node, which also has a null character in it. Now, make head arrow next point to where tail is pointing to, which is this tail node. The initial list is now set up. Push. We declare a temp pointer, which will be the pointer to the new node. Suppose the user now types a C. This is passed to val. So, we call init LL node to create a new node with C in it and temp points to the new node. Then, we make temp arrow next point to where head arrow next is pointing to. Now, make head arrow next point to where temp is pointing to, which is this new node with C in it. Now, we have finished the first push and return to main. So, we call push again and have a new temp and a new val. Suppose the user pushes a B. The B is now passed to val. So we call init LL node again to create a new node with B in it and temp points to the new node. Then we make temp arrow next point to where head arrow next is pointing to. Now make head arrow next point to the same place as temp, which is this new node with B in it. We have now completed the push and can return to main. Pop. We declare a temp pointer and a car pointer, where the temp pointer will be the pointer to the popped node, and the car pointer will be copied from the head pointer. Val will store the popped value. The first node to be popped will be the one with B in it, because that was the last thing to be pushed into the stack. We need to store the popped value because we will still need to return it after the node has been freed. So, we follow car arrow next arrow key and put that value into val. We point temp at car arrow next so that we can find him to free him later. We want to make the head node skip the old first value, so we make car arrow next point to car arrow next arrow next. So now, you can see we have skipped the original first node on the list with a B in it. Because of this, we can now safely free that first node, which is pointed to by temp. Free! Now we have completed the pop and can return to main. If the user now decides to pop again, it will pop the next LL node, which is the one with the C in it. Val will store the popped value. This means that we will now have to store the popped value, so we follow car arrow next arrow key and put that value into val. We point temp at car arrow next so that we can find him to free him later. We want to make the head node skip the current first value of C, so we make car arrow next point to car arrow next, which is the tail node. So the stack is now empty. Because of this, we can now safely free that first node, which is pointed to by temp. Free! Now we have completed the pop and can return to main.
Now that you've seen how we create a stack, we're going to look at the second thing that we're going to do with linked lists, which is to create queues. So in this module, we'll learn what a queue is, implement a queue using a linked list, and after this module, you'll be able to state one application of a queue and draw a VP diagram of a linked list implementation. Write the C++ functions to create a queue, write a C++ function to add a node, and to write a C++ function to remove a node. Okay, the queue is essentially the second simplest application of linked lists. We just have to, we only have to be concerned with two key operators, which is inserting a node at the end of the queue and removing and deleting the node from the front of the queue. Examples of using queues in daily life, actually you've all done it. You've gone to the supermarket to buy groceries and then you end up in a queue. Nowadays you end up in a queue to get into the supermarket because of all the COVID-19 restrictions, right? But in the old days you only got in a queue when you were coming out of the supermarket and you queue up to go through the checkout counter. Also, the human body's digestive system is a queue because it goes in this way and comes out that way and never the other way, except when you're sick. You. Okay, and then there's multi-threading and buffering. For example, streaming audio and video also are implemented with a queue because you want to buffer the input while it's playing, and maybe sometimes the internet is a bit faster, sometimes it's a bit slow, so you want to have some data already ready to play when you need it. So, as last time, we've got these two hobbits, LIFO and FIFO, and we saw that a stack is LIFO and the queue is FIFO. Okay, this module's code. It'll implement a queue of characters with linked lists, and as before, you can always make it implement a queue of something other than characters by just adding to that the record. And we use sections of our previous linked list example, the same record definition, the same init LL node function, and it uses sections of our previous stack example, the same pop function, the same empty function, and almost the same main function. And it changes the push function because now we want to add to the queue at the tail, not the head, right? Because when you have a stack, then you're always adding to the head and you're popping from the head. But in a queue, you enter the queue at the end of the queue and then you leave the queue from the front of the queue, right? So that's why you want to change it to add to the tail and not the head. Okay, what are the key differences between implementing stacks and queues? How do we build a queue? How does the function insert the value at the end of the queue? And what special case does pop fail? Is a linked list the only data structure that we can use to create a queue? All right, so now we look at the code. This part is exactly the same as the stack code. No change. Everything here is exactly the same. Now here is where we find a change, but it's only one line change. We need to add the tail arrow next equals head. That means that instead of the tail pointing at now, we are now pointing it back to the head. And in here, we insert at the end of the queue. Earlier, when we push to the head. Now we're pushing to the tail. So this is the one difference from stack. We are doing tail, not head, right? In a stack, you add to the head, you delete from the head. In a queue, you add to the tail and you delete from the head. So, example run of this, you have the user typing push. You say push what? I'm pushing N, and then push what? Push A, and now I say pop. I get the N, which was pushed first. And I pop again, I get the A, which was pushed second. And I try and pop again, and it's empty, just like last time. All right, let's take a look at the animation of the cartoon showing how this works. You remember the cartoon we saw about stacks? Now we're going to see the cartoon about queues. Are we loading the cartoon? Okay, it's just a bit slow. Okay, there we go.
First, we declare a head pointer and a tail pointer. They are both pointers to struct LR node. Now, we call init LR node to create a new LR node and make head point to it. This is the head node, which has a null character in it. Then, we call init LR node again and make tail point to this new node. This is the tail node, which has a null character in it. Now, make head arrow next point to where tail is pointing to, which is this tail node, and make tail arrow next point to where head is pointing to, which is this head node. The initialized is now set up. We declare a temp pointer. He will be the pointer to the new node. Suppose the user now types a B. This is passed to var. So, we call init LR node to create a new node with B on it and temp points to the new node. Then, make temp arrow next point to where temp is pointing to, which is this tail node. Now, make tail arrow next point to where temp is pointing to, which is this new node with B in it. Finally, make the tail arrow next point to where temp arrow next is pointing to, which is this new node. Now, we have finished the first push and return to main. Then, the user now types a C. So, we call push again and have two new temp and var. The C is passed to var. So, we call init LR node again to create a new node with C in it and temp points to the new node. Then, make temp arrow next point to where temp is pointing to, which is this tail node. Now, make tail arrow next point to where temp is pointing to, which is this new node with C in it. Finally, make the tail arrow next point to where temp arrow next is pointing to, which is this new node. We have now completed the push and return to main. We declare a temp pointer, where the temp pointer will be the pointer to the pop node. Here is the var. Will store the pop values. When the user asks for a pop, it takes the first node. So, this is the LL node with the B in it. We need to store the pop value. So, we follow head arrow next arrow key and put that value into var. We point temp at head arrow next so that we can find him to free him later. We want to make the head node skip the old first value. So, we make head arrow next point to head arrow next arrow next. So now, you can see we have skipped the original first node on the list with the B in it. Because of this, we can now safely free that first node, which is pointed to by temp. Free! Now, we have completed the first pop and can return to main. When the user asks for a pop, it takes the first node. So, this is the LL node with the C in it. We need to store the pop value. So, we follow head arrow next arrow key and put that value into var. We point temp at head arrow next so that we can find him to free him later. We want to make the head node skip the old first value. So, we make head arrow next point to head arrow next arrow next. So now, you can see we have skipped the original first node on the list with the C in it. Because of this, we can now safely free that first node, which is pointed to by temp. Free! Now, we have completed the second pop and can return to main. After last pop node with the C in it, the tail pointer of the list is now pointing nowhere. So, we must redirect the tail pointer to point to the head node by adding below this condition into the function pop. We have now completed the pop and return to main.
Now we're going to look at the same thing using VP diagrams.
This video illustrates the queue program. It is very similar to the stack program, but with a few crucial changes. As usual, we start at main. As before, we declare value and what? Head pointer, tail pointer. Create the head node. Using a temp pointer. Allocate memory for the node. Assign the value into the key. Set the next pointer to null. And return the address of the new node to the head pointer. Then we create the tail node. Using a temp pointer. Allocate memory for the node. Assign the value into the key. Set the next pointer to null. And return the address of the new node to the tail pointer. Point head's next pointer to the tail node. Here is the first difference, we need to point the tail's next pointer back to the head node. Then we print the instructions for the user as we did in queue. In the do loop, we get the user's input. The user typed 1, which means push or end queue. So we ask the user what they want to push or end queue. We take the character they type and ask push to add it to the tail or end of the queue. It does that with the temp pointer. Asking init LL node to create a new node, which uses its own temp pointer to allocate memory for the new node and store the value into its key, and initializing its next pointer to null. Then it returns the address to the new node to the temp pointer in push, which then attaches the new node's next pointer to the tail node and moves the tail's next pointer's next pointer to point to the new node. Then it points the tail node's next pointer to the new node. Now it's done with the push or end queue and prints the value pushed. Since the user hasn't typed 0 yet, we loop again and prompt the user to choose the next action, The user types 1, which means push or end queue. So it asks the user what to push, and gets what the user types. Then calls the push function, which creates a temp pointer, and calls init node, which uses its own temp pointer to receive the new node, and initialize the key and next pointer, before returning the new node's address to the temp in push. Then it points the temp's next pointer to the tail node, and the tail's next node's next pointer to the new node. It then sets the tail's next pointer to point to the new node, and returns to main, which then reports the value pushed. Since the user hasn't yet typed 0, it loops again and asks the user to type the next instruction. The user types 2, which means pop or dequeue. So it checks to see if the queue is empty or not. Since the head's next pointer is not pointing to the tail, it's not empty. So it pops the value off the head by using a temp pointer and a variable val, which retrieves the key from the head's next node. Then temp is used to remember the head's next node, while head's next pointer is advanced to skip that node. Then we free the no longer needed node, and return the key back to the value variable in main, which then prints it on the screen for the user to see. Since the user hasn't typed 0 yet, it again prompts the user for input, and the user types 2, which means pop or dequeue, and so it checks to see if the queue is empty. Since the head's next pointer isn't pointing to the tail, the queue's not empty. So it goes ahead and calls pop to dequeue the next thing, which uses a temp pointer and a val character to store the head's next node's key. The temp pointer keeps track of the node to be deleted, while the head's next pointer is advanced to skip that node. And we use temp to free the memory of that node, and return the key stored in val back to the value variable in main. Main prints the popped value. Then since the user hasn't typed 0 yet, it repeats the loop. The user types 2, which means pop or dequeue. So it checks if the queue is empty. And since the head's next pointer is pointing straight at the tail, it is empty. So it prints empty. Since the user hasn't typed 0, it loops again. This time the user types 0, which means end, which isn't one of the two cases. Since the while condition isn't true anymore, it exits the loop and prints program finished.
In the queue, the init node function and the empty function are identical to the stacks. The push function is not identical because we need to push to the tail rather than to the head. So instead of taking the head, we take the tail, and here we are going to redirect the previous last node to point to the new node, and then redirect the tail to point to the new node. Now, most books use the word enqueue to refer to this, because when we are using queues, the normal name for putting something on the queue is enqueue, and the normal name for taking something off the queue is dequeue. But we left this as push and pop to show you how similar it is to the stack situation. Push and pop are actually the terminology that's normally used for stacks. So compare this with the push in stack, where we had this code here. So it's very, very similar, but only that instead of doing it to the head, we're doing it to the tail, see? The pop or dequeue is identical to the stack. There's no change, and that's why we kept the name pop, although most books would call it dequeue. However, this has one problem which we will find out about later. Okay, what are the differences between implementing stacks and queues? How do we build a queue? How do we insert a value into the queue? in what special case does the pop fail? And is a linked list the only data structure we can use to create a queue? Okay, what are the differences between implementing stack and queue? There's only one difference. In stack, we push and pop from the same end, and in queue, we push and pop from opposite ends. So to convert a stack to a queue, we either change the push to add elements to the tail, or we change the pop to remove elements from the tail. So you can do it either way, okay? And the whole point is that you push and pop from a different end for a queue, whereas you push and pop from the same end for a stack. So how do we start to build a queue? It's pretty much the same as how we start to build a stack, only that since we need to reach back, we have the tail pointing back to the head rather than pointing to now. So this is so that we can refer to the previous thing, because we cannot manipulate this pointer without being able to get at it. So this part is not required for stacks because we never manipulate the pointer before, whereas we always come from the top. Whereas here we are coming from the bottom, so we need to reach back to the previous node. How do we insert a value into the queue? We create a new node, insert it at the end of the queue, and ensure that the pointer tail is pointing to this new node. This is so that we can reach back into the node. Now, in what special case does the pop fail? Well, let's look what happens when the stack empties. Then we will see what happened when the queue empties. When we removed the last thing from the stack, when we removed something from the stack, we had this original node pointing here, right, and coming here. So we would remove this node and it would point straight there, right? So we would have this temp to refer to the node, we store the key, and then we proceeded the temp to the next, and then we hit next equals hit next, so it goes straight there, okay? And then we deleted the temp. So this will go away and this will be connected like that. So when we run the program and we empty the queue, then we can't add to the queue again, and that's the problem that we are finding. So how do we find the solution is we use VP diagrams to try and figure out what's going on. We draw the diagram with two nodes, and when we pop one node and then we pop the second node, and then we see how to solve the problem by showing actually where should the pointer point, and translate the new VP diagram into actual C++ code. So earlier, this was what was happening. We had the head going to 0, the null node, which is the head node, and then it goes to N, and then it goes to A, and then it goes to the tail node, which reaches back to the A here, right? Okay, that's fine. Then what happens when we pop? So if we remove that one, it goes straight to the A. The N is gone, it goes straight to the A. Now what happens when we remove this A? It goes straight to the tail node, but remember the tail node was pointing back at the previous node, which is now gone. Okay, so this is that special case. The last node, when you delete the last node, the tail node is now pointing at nowhere. It's pointing at where that last node used to be, but it's not there anymore. So it's like, oops. That is why once you empty the queue, it doesn't work anymore. So we need to see, what does it need to do? It needs to point back at the head node, right? So if we need to point it back to the head node, we need to have some code to detect that we've deleted the last node and we need to point it back to the head node. So we need to redirect the tail to point back to the head node when we delete the last node. So if the head arrow next, arrow key is null, okay? Head arrow next, arrow key is null. That means the stack or the queue now is empty. So if it's empty, we need to point it back at the head. So we add this if. If from the head we get to the tail, without finding anything in between, then we need to point the tail back to the head. Okay? So, by adding this code, then it works again. So, we can also compress this by putting the initialization straight into the declaration like this. So, just like we asked with the queue, with the stack, is linked list the only way to implement a queue? And you might have guessed, yes, it's not the only way. You can also use arrays. And this kind of queue is a contiguous queue. And this type of queue usually is circular. And what do you mean? Well, take for example the situation of streaming video or streaming audio. You have data coming in from the network and it comes into your computer. Well, the data coming into the network, you stream it into the queue, and the computer is, or your program is taking the stuff off the end of the queue, and so it's a circular queue. See, it goes off that front and it comes to the back. So it's not actually having this the end, but actually coming back to here and filling up. And as long as there's still some spaces, then your queue is not full. Now, of course, in this example, we just have very few bits in this queue, but in real life, you would have a much bigger. But just for this illustration, you see how if you come off the end, you come up to the front, and you continue that way. And so that way, you never run. Well, you can run out of space by filling in all this space, but you have enough space to work with. And that way, if the internet slows down, then it starts eating into this queue, but until it hits the first data item, your audio or video continues to play. And you've seen this on YouTube, where sometimes the internet is cut off, it's so slow, then it starts showing that loading symbol, right? That's what happened. So now you should be able to state one application of a queue, differentiate between stacks and queues, which functions are the same, which functions are different, and use a VP diagram to illustrate a linked list implementation, write C++ functions to create a queue, add a node, and delete a node. And that's it for today's lesson. Bye.